Everybody, and welcome back to my SB2 channel. This lecture is all about the representations of orbitals. I have a quick introduction. We're going to be looking at the shapes of the s orbitals, p orbitals, d orbitals, and very briefly on the f orbitals. And I also have a quick practice for you at the end. Okay, so in our previous lecture, we talked about the wave function and the fact that if you go by the square of that wave function, we can understand the probability distributions of the electrons within an atom, right? That's exactly how we can imagine the shapes of these orbitals, okay? So these representations are going to help us to understand the shapes as well as the orientations of the atomic orbitals, right? And if you remember, we'll talk about these quantum numbers, N, L, and ML, to get all the details about these orbitals, right? The radial probability distribution is one of the common ways to present how the electron density varies with a distance from the nucleus, which is pretty helpful to imagine where the electrons are most likely to be found. Okay, there are going to be a few features for these kind of plots that we have to be careful with them. The first one is the number of peaks. We have the number of points at which the probability function goes to 0, and we call those nodes. That means we don't have any chances to find the electron on those nodes, right? And we also can get idea of how we can spread out the electron distribution, right? Which is going to give us a sense of the size of the orbital. Okay, cool. So the first one is going to be the s orbitals, right? And the shape of the s orbital is going to be spherical, right? Very symmetric, which means that the electron density at given distance from the nucleus is always the same, regardless of the direction in which we are looking at that from the nucleus. It's going to be pretty symmetrical distribution. Very simple, right? Very, fundamental and simple, distributions of the electrons. So as you can see in this picture, we have the electron density model. If you look at the contour models, which is also pretty common, we can get that, the idea of like a spherical shapes for these s orbitals. Okay, so as you can see, if you go from 1s to 2s to 3s, it is getting larger, right? So we're going to be looking at, the differences between these different orbitals, right, in a little bit more details, looking at the next page. Okay, so I'm trying to focus on the radial probability distribution, okay? And I have them for all of these three orbitals, 1s, 2s, and 3s. Okay, so for all of these orbitals, the number of peaks is going to be equal to the n value, okay? And the outermost peak is going to be always the tallest peak. So for example, if you look at 1s, where we have only one peak, right? That's it. But if you look at 2s, there are two peaks, and the outer one is the one that is the tallest one. So we have the highest chance to find the electrons around this area. If you look at 3s, we have 1, 2, and 3 peaks, right? And again, the outermost peak is going to be the tallest one, right? So remember, the taller the peak is, the higher chance to find the electron at that specific distance, right? Okay. The other thing is, for any of these ns orbital, the number of nodes is going to be equal to n minus 1. Okay, so for the first one, I don't have any nodes because the n is 1. If you look at 2s, there's only one node, right? Which means that at this specific distance, there's absolutely no way that you can find electrons, right? If you look at 3s, we're going to get n minus 1, so 3 minus 1, and that would give us 2 nodes, okay? And finally, as the n increases, the electron density becomes more spread, right? And that is something that we can also understand that by looking at these three graphs here. Okay, I hope that makes sense. Now, there's another way that I can look at my distributions of the electrons, right? Which is more about the density of the electrons here, right? And if you look at 1s, you can see that the darker the area is, the higher chance for finding the electrons, right? So this dark area here is where we have, the peak, right? If you look at 2s, you can see that we have kind of gray area, okay, a little bit chance. And then I have a lot darker area here where we get the tallest peak, right, and the highest chance for the electron to be found. If you look at 3s, right, yes, we have a little bit here, maybe a little bit more, right? But look at that. This dark area, this dark circle would give us the best chance to find the electrons, okay? Excellent. Okay, so the next one is going to be the p orbitals, and the shape of these orbitals is not going to be spherical like the one that we have for the s. Instead, the electron density is concentrated in two loops on either side of the nucleus and is typically separated by a plane at the nucleus. Okay, so if you want to think about the shape, you can think about something like figure 8 or maybe infinity sign, right? I know many textbooks mention about dumbbell. They're not dumbbell shape, right? So think about figure 8 is probably the best one, right? And it's pretty convenient to use the x and y and z in our Cartesian axes, right? In order to like label these three orbitals where we have them. For example, here is my pz, this is my px, and this one is py, right? Now, if I have two orbitals where they have the same n and the l, but they have different ml values, this just means that they have different spatial orientation, right? Lastly, like your s orbitals, for the p orbitals, as we get, bigger n value, let's say you go from 2p to 3p, or maybe to 4p, we're going to get bigger size for these orbitals, okay? Cool. The next orbitals is going to be our d orbitals, where n goes to 3, right? And we have L that goes to 2. Okay, so there are going to be 5 possible values for the magnetic quantum number ml, which is -2, -1, 0, and then 1 and 2, right? So here is the names for all of these 5 orbitals. I'm just going to call them first xy, xz, yz, and then x squared minus y squared. We also have z squared, okay? All of these d orbitals are going to have different shapes and different orientation in space, okay? So follow me on the next page. Okay, so on this page, I'm going to be talking about the features of the shapes that we have for these d orbitals, and then I will show you the actual shapes on the next page, okay? So 4 of these d orbitals contour representations have a 4-leaf clover shape where the 4 loops primarily lying in a plane. So 3 of them are the dxy, dxz, and dyz orbitals. And these are the ones that they're going to be oriented in the xy, xz, and yz planes. And their loops are going to be positions between the axes. Then for the fourth one, which is x squared minus y squared orbital, this one is going to be still in the plane of xy, but the loops are going to be along the x and y axes, not between them. Okay, in contrast for dz squared orbital, this one has a very distinct shape featuring the 2 loops along the z-axis, and then we have a donut of electron density in the xy plane. Okay, so it seems that the shape here is very different for the z squared, but they all are going to have the same energy, just like all other d orbitals. Okay, as long as they are on the same n value, same shell, they're going to have the same energy. Okay, cool. And yes, this is going to be the shapes for all of these d orbitals. So make sure that you are able to recognize them. You can see the difference between them. It's more about the distinctions, right, between these 5 orbitals. Okay, excellent. The next orbitals are going to be our f orbitals, where the n goes to 4, and they're going to be 7 equivalent f orbitals for which the L goes to 3. When you're looking at the possible magnetic quantum number, which is the ml, we're going to have 7 of them. So -3, -2, -1, 0, and then 1, 2, 3. Okay. Now the shapes of these orbitals are going to be for sure even more complicated than the d orbitals, and I don't have them for you, right? I'm not going to torture you. I just want to make sure that you are aware of, the presence of these f orbitals. In our future lectures, when we're looking at the electronic structures and the electron density, right, we're going to go back to these f orbitals with respect to what we have in the f block elements, right? But I would say the shapes are not going to be really important, right? We're not going to be focusing on the complexity of these orbitals. Okay, excellent. That brings us to the practice. So I've got a really simple question for you. How many nodes we have if we have a 5s orbital? Okay, so think about it. Your n is equal to 5. Okay, so it must be an spherical orbital because that is an s. But remember, we go by n minus 1, right? And yes, it's going to be 5 minus 1, which is 4. So we're expecting to get 4 nodes for this orbital. Brilliant. A big thank you to all of you for supporting me so far and watching these videos. I hope you like them as much as I like them. And if you want to keep learning with me, just make sure that you subscribe, right? The bigger the channel is, the more work and the more lectures are going to be prepared for you. I'm here to help you with your chemistry journey. Take care of yourself, and I'll see you soon on the next video. Bye-bye for now.